sharing the screen.
Oh, yeah.
Start the recording. Oh. Okay, so maybe we start talking about the interesting stuff. That's not to say that what we did before was not interesting. I think it's maybe very interesting for some of you to learn how to handle data. It's amazing, but of course now we get to a bit more interesting stuff. So today we will talk about embeddings. And maybe some of you already have an idea of what this is, but it's good to synchronize with the knowledge about this. So we will see three things. First, we will talk about how to efficiently encode categorical attributes. So we will not continue to do it the way we did it. Okay? So here, first we will see how we should do it, and that will be like the first case of embedding, but we will not be talking about embeddings here really. Then we will see why this is a special case of what in general we call embeddings, okay? And finally, we will see an example, which is word to vec, which is a specific embedding for texts, and your homework exercise will also be about implementing this, okay? So there will be only two exercises on the next sheet. One is implement this, and one is implement a mixture between these two. Okay, so I hope that the next sheet you will find it a bit easier. But I mean, this is a doctoral course, so I really say we should apply highest level here because this is the most you should get out of the program. And once you pass this course, I mean, this is the highest course we have on deep learning. So there shouldn't be anything really essentially about deep learning that you don't know at least parts after having completed this course. Okay. So for the first part here, what's the motivation? So with the classical view that we have up to this point, I mean, what's the classical view? The classical viewpoint is that we have nominal and ordinal attributes. And the nominal ones we would encode in one-hot encoding, and the ordinal ones with integers or any numbers in reality. So what's the problem with this? So the first thing is that really only because an attribute is nominal, that does not mean that they are all identical in the sense of the task. Okay. So, for example, a nominal attribute is, so what's your legal state? The marital status. Are you married? Are you a widow? Are you in an open relationship? Are you single or whatsoever? So we would treat these as nominal because they don't have an order. But the categories don't have an order, but that doesn't mean that all of them are somehow identical with respect to the task, because if we are doing something that has to do something with couples, then we should treat married people and people with a boyfriend or girlfriend differently from people who are single or widowed. Okay? Okay, so really, like the base idea why we encode nominal attributes through one-hot encoding is reasonable in general. And maybe we want some categories to be more similar to each other than others, even though the attribute is nominal. Not because the attribute itself gives a kind of order between the values, but because for the task, it's reasonable to treat some of the categories in a specific way and others in another. Okay, so one-hot encoding does not really allow for this difference. And now, on the other hand, for the ordinal attributes, so you can have, for example, the education, right? So you have high school degree, like an undergraduate degree, master's, a PhD, and so on. This is an ordinal attribute. And you could encode it through integers, but it doesn't mean that the way how you encode it is in any way reasonable or meaningful for the task at hand. Okay, so ideally we would say, somehow we are in deep learning. We should somehow learn automatically how to represent categorical attributes. Yeah. So in scikit-learn, representing categorical attributes is somehow done as part of the data modeling process. But deep learning basically says you should not make these kind of decisions. It should be just automated, part of the learning process. And the question is, and that even regardless the attribute type. Okay. So now the good thing about deep learning is that we probably don't have to do this anymore because ideally we can really just we can learn the relationships. That's not the case for all of the learning. Deep learning should be possible. So now suppose that we have encoded all of the categorical attributes according to the feature type, like we did before. Yeah, so all the nominal ones went into one-hop encoding and the ordinal ones into integers. Then we have some new dimensionality of the data, which is D. Okay, and all the instances are real valued vectors from the R to the D. So before we had some other dimensionality that was probably smaller than D, but because we have the one-hop encoding, then we blow up with the representation. But the good thing is that we only have numbers. Okay. So this is our point of departure. Now, if we have now a neural network, for example, maybe just with a single hidden layer, then we will train weights and bias terms. So we have a hidden layer of size L, and that will convert these representations. And this is precisely what we can learn. So we will represent instances that previously were of size D. Now we will represent them in something of size L, also a vector. And we also have this doesn't change the shape. It's just like we put them together. And this is really what a very simple, fully connected neural network does. Okay. So in a sense, we see that we can do what we have been doing up to here. And if we just use a standard neural network, then the optimization process should already take care that the representations we learn for the instances are somehow good. So what this slide wants to say a bit is, since we are optimizing, what is a neural network? A neural network is a machine that automatically learns representations. That is really what a neural network does. And if we have this, then really it shouldn't be so important what we did. Okay. We can basically do anything probably. And the neural network, if we didn't make good encoding here, the neural network should just repair that.
That's basically saying it is the same if we label our outputs X, Y, Z and A, B, and C, because the deep learning machine will figure out how to assign those labels automatically, and the algorithm will take care of that, right?
Yeah. So basically, I'm saying, before we say, you should encode the nominal attributes in a one-hop encoding, and for the ordinal ones, it's important. Like, for example, if a higher degree is better, then maybe the number that you assign to a higher degree should be higher than the number. And what I'm saying here is, if we use a neural network, and this should be really, it shouldn't matter at all, because the network should just repair if you didn't do a good job in the encoding. Now, if you do a good job, maybe you make it easier for the network, doesn't have to repair anything, but this shouldn't be necessary anymore. Or it doesn't matter. So you could even go and encode nominal features with integers, which is really not meaningful in general. So you shouldn't do it. But here, since we anyway learn new representations, shouldn't be a problem. Okay. So if we think of this in a figure, then we could say, okay, we have a number of categorical variables. And now I only talk about the nominal ones here because the others we just convert into numbers anyway. Okay, so the ordinal ones already went here somehow, and the categorical ones we turned into one-hot encoding. So like here, orange is like the original data frame, and maybe after after label encoded ordinal features, then we do a one-hot encoding for each of them. This gives us kind of new data frame. But once we have this, we can just train a linear layer, a neural network, and we get here at the output, we get new representation of the instance. Okay, so far so good. Now, why is this not so good? So, yeah, what would you think? So in principle, this argument is correct, but maybe if we do things this way, in general, there are two things that are a bit suboptimal about this approach. Any ideas?
Some semantic relations of the
Yes,
data.
sure. I mean, if we are considering that
Yeah, but wait, what the semantic relationships between the data, so, but was that already a sentence? So what would be the problem? Or maybe a concern?
You're asking about the previous.
Yeah, so I'm thinking about this. Like we can do this. Actually, this is what you have been doing so far, probably. But why is this maybe not so good to do this?
the number of parameters.
In America, estimated.
Yeah, the parameters. Because if you use one hot encoder, you create new variables, and each of these variables requires a parameter to be estimated.
Yes, that's correct.
And you have more parameters to estimate, and maybe your data is not huge enough.
Okay. Yeah, sort of. So that's maybe one point, but essentially we will not be able to solve that problem, probably. But
I was talking about the semantic, but the thing is that when you do some one hot or whatever representation you lose information about the sequence, the order of those categories.
yeah, but this is the order should not matter if it's nominal. So if they are nominal, then they don't have an order because it's a nominal feature. If it's ordinal, we have it already this number down here.
I believe if
Okay.
no worries. If we are using, for example, one hot encoding, I'm wondering what happened with the linear layer in that spectrum between 0 and 1. Are we losing like some sort of a state space because of the representation we are using?
Not necessarily because, so you mean because these are on different scales than these guys? Yeah, but this is, this can happen, but this probably shouldn't be a problem because somehow you have individual weights for each of these variables and then you can adjust this. So all of this is really not yet so much the argument. So, okay, so let me explain to you what the issue here is. I mean, you can do it, but so first of all, one problem is it goes a bit into what Wilson said. It's not so much about the parameters, but about the number of variables. So if we do this and we have we have some variables with a lot of categories, then we will expand into a huge vector because like you have 500 towns in Colombia that are registered in the database. And for each of the towns, you have one variable, then this blows up your data representation.
But you can avoid that with binary code. Not You use
Why
one hot to
creating
use
doubles
binary.
of terms and you do not have a specific way of reading them?
What do you mean? I mean, if you have a categorical attribute with 500 values,
Yeah, but how many bits do you need to represent a number of 500? Not 500 columns. You need less binary.
yeah, okay, but
bits.
now you're already, but this is equivalent to encoding the town with a number.
With a series of bits. So you are avoiding that spread of.
Yeah, but this is the same because a number of bits is a sequence of bits is a number. I mean, if you do this, you could also just store the number represented by the sequence.
Yeah, but when you do dance in Python, you're doing kind of the same. You're
Yeah, I already know the solution, so I mean, we're talking about something similar. I'm just saying that
Yeah,
if you do
I know.
naively, if you do naively, if you use one-hot encoder in scikit-learn,
yeah.
you get a 500 column blow, and almost everything is zero.
We have 1,000,
Yeah,
we have 1,000 nodes.
my point is that that is the works scenario, because why the libraries don't use binary encoding, not what?
Yeah, because they also shouldn't use binary encoding. There's an even better solution. Yeah, so we will talk about a better solution that is better than binary encoding. But this is like one issue that's going on. And by the way, binary encoding, which type of variable would that be? Is it a text then, or do you treat it as a number?
Yeah.
Yeah.
No.
Because then you also need an algorithm that understands this kind of representation, right?
You need the data type.
Yeah, you need a data type for this. But I mean, of course, it's I would probably assume that what we are going to do is probably the same as what you're suggesting. At least it ends up in the same solution. And the other one here is, let's go back to the figure maybe, and we will see that really this W, this weight matrix, is really combining everything in an instance. So it's not only encoding certain categorical attributes, but it's encoding everything together, right? So this W is not only like creating a numeric representation of this variable or this variable, but somehow of everything together. So this is okay. It's not necessarily a drawback, because if you just want this for your task, it's fine. But maybe you say, okay, but here I have a variable that I also need in other contexts. So why not, if we already make the effort to understand how to represent this attribute as vectors, why not isolate this and modularize this so we can reuse it later in another context? Okay. So this is something that we cannot do if we put everything together. Okay. So from these two aspects, we could define two requirements. First, we don't want to have an explicit one-hot encoding. We don't want to blow up of the number of columns. Okay, and we also don't want new data types. And the second requirement is that we somehow want to modularize things so that we have such a numerical encoding for each of the categorical variables and not just one big mess. Okay, so the second thing is somehow easy. So how would you do this? The second requirement to satisfy is somehow easy. How would you do it in this case, maybe?
You repeat it again, the second.
So the second one is to say, I don't want a general W for everything, but I want a numeric representation only for this variable, for the values in this variable, and also only one in this variable, and also only one in this variable.
Can I type in individual weights?
Exactly. So what you can do is that you will just have a linear layer for each of these. And then another one here where you aggregate everything. So that is really easy to do. So you say we have default The dcat is the number of categorical variables that we have, okay? So what we could do would be to train this number of linear layers, one for each categorical attribute, okay? And in the end, we aggregate all of these together with the numeric ones of X. So that would be something like this. Okay, so here we have a linear layer for each of these, and then in aggregate means also this could be a linear layer, it could be something else. Here you start basically using everything together. So like the concatenation of these guys here is like the new numeric representation of what we have. But we have like disentangled now with the layers, because now we have specific representations for this, and this, and we can reuse this in another context.
So that's my question. How can you reuse those weights in different applications? How you can like separate?
Technically, you mean?
Yeah.
Yeah, in PyTorch, you can just download the weights of each layer after you trained it. So if you trained it, you can download it. You can save the module and you can inject it again. So yeah, we didn't do this here, but in the deep learning course, I showed how you can download or you can serialize certain modules with their weights, and then later you can use them again in another context.
And practically, you learn a feature you want to take it from this network to this one. How do you use that?
I imagine that you have another data set, or maybe even you have the same task somehow, but you want to work with different versions of your data. And you don't want to learn this every time from scratch. So, like, I don't know, maybe you have bank data and you want to see, okay, what happens if I add a certain feature or I take something away or something like this. So for the different like versions of your data, you can then reuse this layer each time again. Instead, like you train it only once in one context, and then for the others, you just take this again, so you don't have to learn it again. Yeah. So it's not an arbitrary context, but it could be also a completely different task. Yeah. Because I mean, here, I mean, how do you define this network? You write in PyTorch, you write a new module, where you say, I have this, I have this, I have this, and I have my other stuff. This is part of the definition of your module. Now, what you can do is that you will just, instead of saying, here I have a new linear layer, you will say, for this, I use a linear layer, you load linear layer that already has weights. What's the difference? The difference is that instead of having a random initialization, you have an initialization that comes from a previous training process.
But you don't want to pass this linear layer to a retraining because you are going to modify it, right? Or maybe you want.
And you can, so you could now freeze it, or you just say, I take what I had before as an initial weight, which is better than random. You can do both. Okay. Good.
Sure. There's something that I do not completely understand, and that's the fact that when you say that you are doing an aggregate, that couldn't be considered essentially a layer. Or you're creating like another little layer for numeric features and then just literally just adding them.
No, you don't. I mean, you could, in principle, you could add. So aggregate means somehow you put things together in some way.
Okay.
It's not said how you do it. It's not like we are summing it. It could be a sum. Okay. But what I said before is that a typical aggregation would be concatenation. You take this and you add, but not in a numerical way, but you combine that, like you stack these onto each other. Like if you have 10 features here and 10 features here and 10 features here, then you have 13 new features. You put them together. You could also add them up, and you have only 10 features. These 10 plus these 10. Sometimes it's also enough. Okay. Plus you have the features that come from here. So this just means from here on you do whatever you want. Like whatever you want. So after this, you have your numeric representation.
Like a linear layer, for example? A linear layer?
Yeah, could be a linear layer. Exactly. But then in this linear layer would have, for example, 30 plus something inputs. Yeah, all of these. And then what you have to do in the forward, so if you make that this is a linear layer with like, let's say these are also 10 features, then you have 40 features in total. Yeah. 10 from this encoding here, 10 from here, 10 from here, and 10 from here. And in your forward function, you have to stack them together, and then you can put them into this linear layer. Actually, that's what you have to do. Okay. Now, what I now want to do is that we look a bit at this linear layers, because actually we could do this, but if we now talk really about having linear layers only for like encoding these types of variables, we should do something a bit smarter than this. Okay. So if we look at it, let's look at what happens here. So if we use this linear layer, I mean, what's the input of this linear layer here? This is a one-hot encoded vector. So whatever we have, the input for this guy will always be a vector that has only zeros, except in one position it has a one. This we should exploit because this has an important consequence. So the input is a unitary vector, EI, where I is the position of the one, right? So the output of the linear layer is this here. We multiply the weight matrix with the input signal, but since the input signal is only zeros, it's just one at one position I, we can write it like this, plus the bias term. Okay, so this is the output of the linear layer. But I mean, what is a multiplication with a with an identity vector? It's just like I extract the ith column from, because for the first column, for the first row, I only have multiplications with zero. Only at the ith position, I multiply with one. And then I take the value that I have here. And for the second row, it's the same. And for the third row, it's the same. So in the end, I only take always the ith value from W. And that means I extract the ith column from W. This is what this layer does. And after this, I add a bias term. But why do I add a bias term? I mean, now let's use so let's say I have 5 possible categories in my output layer size. So let's say that W has only 2 2 rows. Okay, so we map here into 2-dimensional space. And before we had 5 categories. So then these 5 categories would now be 5 points in a 2-dimensional space, right? Now, what is the effect of the bias vector? The bias vector will just basically move this class. So this would be like, let's say for B equals -1, -3, okay? And now for, let's say B equals 0, 0. So if we don't have this, basically then this would move a bit. So exactly sure, but would look something like this. Okay, so the organization of the points would be exactly the same as before, only their position, like at the position of the whole column moves a bit through this bias term. But this seems unnecessary because really what the encoding is for is to create certain distances between the categories, but not, I mean, the position in the space somehow doesn't matter. We can also have it here or here. I mean, what's the effect? Doesn't matter. Okay. So somehow it seems like when we're using a linear layer for this type of encoding, we shouldn't learn a bias term because it's not really helpful. We don't have activation functions here. So we don't want something to pass a certain threshold or so this is why we don't need an intercept. Do you understand?
Mm-hmm.
Okay. Okay, so we have two things that are a bit odd here. First, we are doing a matrix multiplication, which is expensive, where we really only need a lookup of the ith column of a matrix. So I mean, looking up a column in a matrix, this is almost constant time, and matrix multiplication is expensive. It's like the runtime is the square of the size of the matrix. Okay, so this is one inefficiency, and the other is that we add bias. Well, this is not expensive, but it's necessary, and we're learning parameters that we don't need to learn. Okay? So in this case, we would be learning two parameters here for B. The first and the second that we don't really need. Okay, so for these two reasons, we shouldn't use a linear layer, because linear layer does what we want, but it's not very efficient. So what should we use instead? Well, there's nothing that we can use unless somebody has developed this for us, and gladly in Python they have developed something for us. So we would just get the same effect if we can create our own layer where we just say, I get like a categorical value. Before talking about the solution, so let's just summarize again. If the input is the one-hot encoded vector EI, basically what we just want is that we return the ith column of W. That's all. Without the price, only this. Basically, and this is the same as a linear layer without bias. Okay? But here we should think of this really now like a lookup. We're not doing any multiplication anymore. We're just saying, this is the input, then give me this column. End of story. But if this is like we want to do it, then we don't even need the EI. I mean, where do we use the EI on the right? We only need the I. Okay, so we don't need to know that's vector number E17. We only need the 17 because this will tell us anyway. We will map this one hot vector with the one at position 17 to the 17th columns of this guy. So we don't need this one hot included anymore. Okay. So this means that we can basically the solution for the second problem implicitly also solve the first problem, because the first problem was second was modularization. First was we don't want these blowouts anymore. But if we use this technique, then we don't need one-hot encoding altogether. We just, instead of doing one-hot encodings, we just store, this is category number 17. Or number 3. Okay, so we can use basically label encoding for all of these, also for the nominals. The important thing is that internally, so now we replace the category with a number, as we usually only do for ordinal encodings. But the point is here we don't use it like an ordinal encoding. The idea of this layer is to use this index as if it was nominal, because this is just a shortcut. This lookup is a shortcut as if we did one-hot encoding and matrix multiplication. Okay, so this is a bit confusing part because sometimes one thinks, okay, I'm now starting to encode also nominal attributes just with integers. And that's true, but that doesn't mean that we treat it ordinally. It just means that this number. What's the meaning of this number, 17? It's not like we give this like the value 17 to this category. It's just like an index of where do we find the representation of this category in our matrix. Okay, so it's a kind of map. It's not like, really, it's not like 17 is more than 13. 17 is just another index in this matrix at 13.
Special location. Maybe this is confusing because it's just one dimension. When you go to several dimensions, you understand that it's a location in the space.
But this will always only be in one dimension here. This is only one dimension because it's just basically the location in your weight matrix.
And
I think that, like, I'm thinking in the example, I want to know if that's correct. Let's say, for example, you were using the example of like 500 towns in Colombia. Like, there's over 1,101 municipalities in Colombia. If I wanted to do like a neural network using that variable instead of creating a blow up, as I understand why using one coding, we could just use like any number, just going from 1 to 1,000.
you
Just
will
use this.
numbers from 0 to m minus 1, where m is the number of categories. I mean, here I write like in the mathematical notation, it's 1 to m, but in Python it's 0 to m minus 1 because this is really an index of tensor.
What I want to know is how could this happen without creating arbitrary relationships that are going to mess up the model?
Yeah, the point is that these numbers are, it's not like you say, this is really the value of the category. It's just saying, so I mean, to understand this in depth, it's maybe good to study again these two slides. But what you really need to understand is that this is only a shortcut for doing one-hop encoding and then a linear layer. So
Okay.
if I say one-hop encoding plus linear layer, you would not ask this question. Because you would say, okay, it's one-hop encoded, it's nominal, there's no arbitrary relationship. So this is only a shortcut for doing exactly this.
Mathematically, they like those two groups of
It's exactly the same. If you do this, or if you do first one-hop encoding and then do a linear layer without bias, it's exactly the same thing.
okay. Like, I think that there has to be like some really complicated mathematical proof of that, right?
Not at all. This is the mathematics.
Oh, that's great.
So this here is the argument. Yeah, but you can look at this with some calm. I will admit that I found this confusing myself when I first saw it because I said, I mean, why will you label in code the nominal attributes? Because then I create arbitrary relationships, but this is not really happening. But to understand why it's not happening, it's important to understand this. And now, happily enough, in PyTorch, they have created a layer like this for us that does exactly this. And this is called the embedding layer. Okay? It's a module and it receives two parameters. The first one tells us how many categories exist. It's not how many variables, it's not how many categorical variables exist. It's for this variable, how many categories exist. How many towns do we have? Okay, so this is just a number. And that will tell him I need this number of columns in this weight matrix. Okay, and then it will tell, and this here says to which dimensionality, in which dimensionality do I want to represent each of these? For example, here I represented 5 categories. So the first thing would be 5. Okay? Number of categories is 5, and I represent them in 2 dimensions. Then the embedding dimension would be 2 in this case. But here I can also say I want to represent them just 1 or in 5 or in 5. Okay. And then the input of this layer will be integers. Okay. So maybe these 5 are like high school, college, undergraduate, master, PhD, I don't know. And I assign numbers to each of them. 0, 1, 2, 3, 4. And the input for my layer are these images, these numbers. So this layer here does not receive strings also. You cannot receive like a collect. So you have to previously encode this with integers, and every integer represents a category, and this goes into this layer. And the output are then the numeric representation in real value.
Wondering why we don't use the same number of categories for the dimensions of the embeddings.
Yeah, that's a good question. Because then you don't really have an advantage.
So, I mean, that's exactly why we wanted to get rid of one-hot encoding. So if you have one-hot encoding, then you have 1,000 categories. And this here is the size. So this here is really the size, the dimensionality of your data in this aspect. So now what would happen if you say I have 1,000 categories and I'm embedding dimension 1,000? Then you save yourself from having to do a one-hot encoding before. You don't have these 1,000 columns, but now you create these 1,000 columns here with your embedding. So what's the game? Okay, so the idea is to we will discuss this number of dimensions in a bit. So what would be the choice here? We will discuss it, but so what we really get is we do not use a linear layer here, but we use an embedding layer, and we use an embedding layer for each of the variables. Each of them has a separate embedding layer. Okay, good. So now that we have this, we can think of trained embedding layers like shareable modules. You can download them and you can share them. You say, okay, you want to encode my racial status or all the education, and here I have a module for you. And you can use this, and I already have good representations for this. Okay, and that's cool because then you can take this out of the learning question. Okay. Yeah, I said this, but what is now more important, and in fact, like this idea of learning representation separately, this is really, I would say, one of the most important transformations in machine learning in the last 10 years. So what we just said. Why? Well, if we're talking about the level of education, okay, we can share this. But if our categories are now like words in natural language, we have 20,000 words in a language, then having a great embedding for words, this is really something that you can share with a lot of people and they will be eager to use it, right? Because with a language, you have to work, everybody uses a language for something. So this is a very broad case of application. Right? So this is a really important achievement. But what is also interesting here about this modularity now is that we say, okay, but if we think of embeddings like models that we can share, we could just also, so this is a kind of creating an interface. Someone wants an embedding for words, for towns in Colombia, doesn't matter. So if people could be interested in this kind of embedding, I could offer this as a service. And I could train good embedding independent of any task, just because people want to use this.
I would like to get deep into that. That's just really interesting. And let's say, like, just go again with the type of challenge. Like, training and embedding is like trying to put the concept of like this town in relationship with all of the other things. And that's what is
all of the other things, only the towns across each other.
Okay.
So what's the relationship between towns? So you would have, maybe you want to say, I have 1,000 names of towns in Colombia, and I want a numerical representation for them, a vectorial representation for each of them. But I mean, I could do something random. I could just map them into random space, but I want that this is somehow meaningful. Okay, so that somehow towns that have something in common are closer together than others. This is a difficult question a bit. I mean, how can you then train this? But this is the third part of the class. So let's just leave it like this for the moment. But the cool thing is that we can now see this as something modular. Okay. So that was now the motivation for the whole thing, coming from the category. Now it's actually, I haven't been using the word embedding on its own up to now. I've only been talking about embedding layers. And I've used this word only to say that this is what PyTorch offers, okay? But actually, what an embedding is a bit more general of what PyTorch names an embedding. So this, if we look at PyTorch, then we see that there is a class embedding, but actually an embedding is more general than this. This is only a very specific type of embedding here. Okay? So this is the embedding layer in PyTorch, but an embedding, what's an embedding in general? So now let's say that we have just any set O of possible objects. That can be any set, can be finite, can be infinite, can be structured, whatsoever. So we have some set of things that we want to represent. Okay, and an embedding is exactly that. It's a function that takes any object and maps it into a vector. This is an embedding. So what we saw up to this point is actually just a special case where O is a finite set of atomic objects. Right? So O could be a set of towns, or a set of levels of education, or a set of images. Anything. So up to now, we just had a situation like this where these C1 to Cm are like atomic objects without specific order relation, structural relationship, like categories, okay? But O can contain also like graphs. So for example, O can contain social network, for example. Or connections between stakeholders, for example. O could contain an optimization problem, for example. So how do I encode an optimization problem like a traveling salesman problem? Yeah? Or a chemical component, yeah, like drug components or whatsoever. So we're saying nothing less here than we now want a mechanism that can take whatever kind of thing and put it into a vector. And any function that achieves this is called an embedding. But we cannot use the PyTorch embedding layer for all of that. So the PyTorch embedding layer only works for this simple case. But in general, we want to be able also to encode other things. So now, what are desirable properties about it? Because I mean, it's just any function. So, so as I said before, I could now take, for example, an object like I could take this object and just assign them random vectors. That would be an embedding. Okay, but is this embedding useful or not? No. So I take some social network and I put it into the vector 3, 4. Or I take images and just assign random numbers to each of them. Well, random already sounds disturbing because random means that I basically lose the information I had before. So it shouldn't be random, certainly not, only to have a vector. I mean, I will not get a real valued vector at the cost of losing everything I know about it. So somehow it should still preserve knowledge, okay? It's not a formal requirement because any function that is technically an embedding, but we have some, like a catalog of requirements. So one thing is semantic similarity. Semantic similarity should imply geometric closeness. That means if two objects are similar in what we understand by similarity, then somehow in the vector space, their points should be closer together than other objects that are not so similar. Okay, this is also closely related to kernels, right? So
Related to what?
kernels.
Okay.
So semantic similarity here means similar in the sense that they are similar with regard to what is relevant for the task. Yeah. So it's not in general to say, yeah, okay, but maybe being single and being a widow is more similar to each other than being married or having a boy or girlfriend. Okay? Then we want them to be low dimensional but expressive. So we precisely do not want 1,000 columns, but we want ideally just 1, 2, or 3. But they should really be useful. So the less dimensions we have in the embedding, the better it is in terms of use. Like, so we should try to minimize this, but it should be still enough enough dimensionality to express what is important. And I will in a bit explain you why this is a trade-off. Okay. Then there are things like compositionality. This is a bit strange, but so there is something like. So let's say that the embedding function is f, okay? And you can say that you have f of king. King is embedded into a vector, okay? And if we take away from king the man, and we add a woman, then what would we maybe get? Queen. So this is like a classical example where you say you have some meaning of a man, you have an embedding for man, for king, and for woman, and for queen. And in this representational space, you want that you can a bit move around semantically. Okay? And if you take a king, which is basically a man who is the governor of something, and you take away the man, but you replace it by a woman, then you get a governor of that something that is a woman, and that is a queen. Sort of. Okay, so that is a bit like this idea of this is where you would really have semantics, right? You have this kind of thing.
It was until you use moon and sun in your.
And then we have transferability. Transferability means that this is basically the usefulness across use cases. That hopefully this embedding is useful for many situations, many downstream tasks. Downstream means, so think of the river. We are at the start of the river, but at the end of the river or down the river, we want to do other things in our neural network, okay? So depending on what we want to do, and I would say, okay, the embedding is a component we can use in different neural networks, and hopefully in most of those, these embeddings are doing something useful for what we want to do later in the river. Okay. And importantly, they should be. They also should be aware of the structural aspects. So, for example, if my object that I want to embed has, let's say, it's an image of a car. Where it has some pixels in the middle that show something red, then like having an image that has a lot of red pixels that are closely together should produce a significantly different embedding than another image that has the same number of red pixels, but these red pixels are distributed all over the place. So this closeness of things should be also represented here, okay? Or for example, if your object is a graph, then nodes that have a lot of neighbors should be closer together. We have two influencers in the network, they should be closer together, maybe than isolated nodes. Okay? So this structural awareness. All of these are a bit like soft requirements, not like we can measure this super well, but I think it gives us an idea of what we want, right?
You're sorry, what we did say that it's the difference between structural awareness and compositionality. What is the difference between compositionality and structural awareness? Because I think that both of them are related to the idea of trying to get those
compositionality doesn't really talk about the like, you know, in this example here, there's no such thing like structure. My objects are just words.
Mhm.
Yeah, but I could have that my objects are nodes in a graph. And I have one node that has like 4 neighbors, and I have another node that has 1,000 neighbors. Okay. Now the node is basically the node itself is basically what you want to embed. The name of like the index of the node. It's like the identity that you want to embed, maybe. But you don't want to use only the identity of the person, but also other things that are relevant. How many messages did this person send, for example? And this is like, so this is here like the part of the structure. So structure is the structural part of the graph is this here. Okay, so the red part is the structure, and you don't have this in this example up there. So this would be, you want to take into account not only the object description itself, but also proper structural properties of this object in the context.
Okay.
Yeah, and this is not the same here in the compositionality. It's more like different. It's a different type of property.
Okay.
Now, what's good size for the embedding? Now, one interesting thing is that if my set of objects is countable, that is maybe it's finite, I have a finite number of categories, or it's infinite, but I can still count it. So, for example, the number of the set of natural numbers is infinite, but it's countable. So, for any number, if I can give an algorithm that will enumerate any number after a finite number of steps. Okay. I cannot give such an algorithm for the real numbers. So the real numbers are strictly more infinite than the natural numbers or the rational numbers. And that makes it continuous. So unless I have, so if I don't have anything continuous, just finite or infinite, well, actually I can put anything just on a line and make it separable. Okay, so for example, here, if I have 5 categories, I could just say my embedding is just one line, and I put category 1 here, 2, 3, 4, and 5. I just put them onto a line. And if for some reason I need to move them because I want a different order with it, I will learn in my representation that, well, okay, this doesn't go here, but actually it goes here or so. But I can learn this. Okay, this will be part of the learning. So then really the question is, if I only have a categorical attribute with 5 categories, why should I even do anything else than just one? D equals 1, like for the embedding here. Any idea?
More information.
Some
Some
and how,
nuances of the
huh?
some nuances of the
Yeah.
position.
And how is information essentially being represented in data? That's the core concept to measure or to express information in some. But distances between, and so this is what I said from the first class in machine learning, that the most important concept in machine learning is distances between vectors. So here, and now, the lower my dimensionality, the more limited I am in expressing certain properties of distances. So look at this here. I have 3 points. And now my task is, how can I position the 3 points on a line so that, actually I want to treat them in a nominal way. The distance between each of them is the same. I want that the distance between A and B is the same as the distance between B and C, and the same as the distance between A and C. Is this the case here?
A and C, no.
A and C don't have the same distance, and actually it's not possible. If I only have one dimension, I cannot put 3 points onto the line so that they have all the same distance. So this means that if I want now to really express a nominal condition that the distance between all of them is identical, I can't do it on just a line. Okay, so I cannot encode the nominal or the indifference property between 3 points if I only have an embedding size of 1. If I have now an embedding size of 2, I can do this. Yeah. So that tells me what you said. If I want to encode nuances about, if I want to encode more information, and information is distances in a vector space. If I want to do this, then I need a certain dimensionality to capture it, to be able to capture it. Yeah?
So if I have more dimensions, I have.
If you have more dimensions, you are able to organize your data so that they represent more information. Yeah. I mean, it's not a guarantee, it's just you give a possibility. So in general, for a certain number of points, so if you have k points and you want them all to have an equal distance, you always need a k minus 1 dimensions. If you have less than k minus 1, you cannot do it. Okay, so this doesn't mean that having more dimensions is always a good thing. It's just like giving the possibility to organize things. So having a small embedding space is restricting your possibilities. This can be maybe a problem. So there's the trade-off. We want to have a small number because this is more convenient for computational reasons and also for another reason, which is to prevent overfitting. Because if you have too many dimensions, we can basically fit specific representations for each possible point, which is also not so good. So there's somehow this this trade-off we need to solve. So based on the previous, one could recommend, okay, choose D as large as you can, at least large enough. We don't know really what is large enough. But like having more dimensions gives you more possibilities and gives you more freedom. That can be an advantage in general, okay? But this implies more complication, so maybe we don't want it for this reason. And the other thing is that you have this overfitting problem. So somehow we want to have a middle ground. And one recommendation which I actually see is that at least if you have a finite number of objects, like categorical attributes, that you would use like the square root of this. So then you have a significantly smaller number. So imagine like you have 10,000 pounds, then the square root is only 100. This is significantly smaller, but it's also not super small, so that you can still have enough like space available to represent this variety. Because the more categories you have, maybe the more dimensions you need. Because as I said, if you have k different, if you have k points, you need k minus 1 dimensions to model a nominal case where all of them have the same distance among each other. But probably you will not need this. So you did not size of O minus 1. That would not be a great gain. But if we have square root, it seems like a kind of good trade-off. It's not really, there's no theoretical reason, or so it's just like a kind of, okay. Good. So what kind of embeddings are there? This, I will not expect you to know all of this, just like to give you an idea of what's happening. So what do we have embeddings already? We can embed words. This means static embedding. We will talk about contextual embeddings when we talk about encoders. That comes later. So we can embed words, natural language word, or sentences. We can embed graphs, already images, and we can also embed combined things like video clips, for example. Like videos, which are a combination of images and sound. So basically, we can embed anything. But of course, if we come with new type of objects, we have to define how the embedding works. The only thing that comes already predefined is like the basic one, where I have a fixed number of categories and I map them. So this is the simple case, it's the only one that is predefined in PyTorch. But of course, for several of these, also libraries already exist. Okay. But somebody made the. So the point is now, embeddings seem super useful, and they are super useful, but they are not really straightforward. What this means, or in general, at least not if you start from scratch. If you want to train new embedding, this is only straightforward if two conditions are met. First, only if the number of objects is finite and the objects are atomic. In other words, only if your attribute is, or what you want to represent is a categorical variable. The first thing. And only if you want to do, only if you want to train a specific representation for your task at hand, not a general one that you publish to other people. Only if you have these two, it's easy to do it, because only in this case, you will say, I use the PyTorch embedding layer just as part of my network, and then I train. But if one of these cases is not met, then you can do this. The first one, if you don't have, okay, so I think that's the second one. So yeah, no. So if I don't have the first one satisfied, then I cannot use the PyTorch embedding layer, because the PyTorch embedding layer needs this thing. And if I cannot use the PyTorch embedding layer, then how do I then create this mapping between an object and a vector representation? How do I do this? So you want to have a mapping between a PDF document, and you want to embed a PDF document as a vector. How do you do this? This is not something you can do with a Python and PyTorch embedding layer, because you cannot count, like you will not assign to every PDF document a number. Not every PDF document is its own category. It doesn't make sense to see it like this. So in this case, how would you even, so what you need to do is that you need to write in PyTorch your own module, your own layer that can take as an input your PDF document and outputs a vector representation. How would you do this? Difficult task. You can write PhD thesis about this. So this is what makes existing embeddings for complex objects so valuable, okay? Because it's not easy at all to come up with your own embedding for any type of objects. The other is, okay, even if you're have a categorical attribute, so let's just say, the 1,000 towns in Colombia. How would you train a good embedding for that if you don't have a concrete task at hand? So you want that, I don't know, Chia is close to Popayan. Geographically, of course, but for some reason, maybe it's good that these two appear close together. But how would you try to get this embedding? Okay, so the question is really, if you don't have a concrete supervised learning task, what's the loss function you want to optimize? There's no such thing like the correct answer. Okay, so this is maybe a bit of a tough question. This is very such out to the third part for words. So here the task would be, I want to create a nice embedding for words, so that words that are somehow more similar to each other are closer together. And we will now see one of these nice pictures that you have already seen, certainly in some context. Okay, so I will show you an example with food. So we have a vocabulary of size 6: burger, pizza, and pasta. And we have car, bike, and bus. So it seems like these three vehicles should be somewhere and the food should be somewhere else. They should be like mixed together. Now, how do we train such an embedding? How do we get, I want to have now a two-dimensional embedding like this, of these words, but how do I train such an embedding? How do I tell it? How do I tell the network exactly this? I want some of these words to be closer together than others. If I don't have a concrete task, I don't have a classification task. 10. So if I had a concrete classification task, then implicitly a good embedding would be learned just as part of my standard supervised learning task. But I don't have a supervised learning task. I just have I want to learn a good embedding so that other people can use my word embedding. So example, we need to create data because probably, I mean, I'm not even sure, but this is how it's currently done. Okay, so we're now talking about how do I create an embedding from scratch without a concrete supervised learning task at hand. So how do you do this? In this concrete example, and this is important because you will implement that at home. Anything I say is important. So we start, what's the input? But at least we should have some text available, okay? So let's say that we have a corpus of text. This corpus, and all of the words here stem from some vocabulary that we call B. So B is basically now my set O, the set of objects that exist, the words that exist, okay? And now what we do is that we define a set of positive pairs, WC and WO. So WC is called a center word. This is a word that we find somewhere in a sentence. Okay? And context words are words that appear around this word. Yeah? So you have a window size, maybe 2 or 3, and you ask which words occur around car. So I have the word car, and then before I have some words, after this I have some words. Actually, I have some example here for you. So we have a sentence, the cat sat on the mat. Very good. So here we have a word cat. This could be a context word, and each of these will be a center word at some point. Okay. Now this is my center word, and which of the words occur around this for a window size of 2? Well, this here, this, and this. So I can have for, yeah. So I have, okay, so for the Windows size, I only look at windows of size 2, including the center word, okay? So here I have a window of size 2 that's like this, the cat sat. And from this, I can infer then different context words, okay? And what I now do is that I use every word that occurs in any sentence once as a center word, and I combine it with its context words. Okay, this is a 2-nested for loop. First for loop is go over all the sentences. Within each sentence, go over all the words, and for each word, combine it with all the words that appear in a window with this. Okay. And these, if I do this, this creates pairs, and these pairs will be my data set. So my data set now is pairs of words. And in addition to this, but this is only positive training habits. Now, positive does not mean like they have a positive class assigned. It's not like binary classification. Positive here means just like, yeah, they occur together. Okay. And now we also want to have like negative samples, which are like combinations of words that do not occur usually together, or at least like we contrast it a bit. So we can take any word and combine it with any other arbitrary word from the vocabulary. Okay, and that would be a negative example. So negative example or negative word would be W minus. Okay, so we have 3 symbols here. WC is for the center word. WO is for the context word. Okay, so this has to do something with this. And WEI minus is a word that is not related to the center word. Okay. Now, if we have this, then we can employ training procedure. So what we want to do is we now need to embed everything because we have different words. Words are like categories, right? So we can think of them like numbers, and then they map to one of the columns in a weight matrix. This is again like the first part today, where I have like, I just look up different categories, and my categories are words, word representations. So I'm embedding my words in d dimensions, for example, 2, because I want to visualize this. Okay. And for each of my words, I have a 2-dimensional real value vector that tells, okay, I will write the word like this. I will use 2 such embedding matrices, one for the center words and one for the context words, because somehow these are like 2 different roles. It's different to treat a word like the center of something or just as a context of something, okay? So we use 2 different embedding matrices here. And then we define a loss function that is not related to any specific task, but what we want somehow is that we can correctly say, or that our mapping makes sure that that more similar words are put closer together than others. How do we do this? We use the dot product. As you remember, I will not repeat this because I will not explain this in depth because I do this in every course, and you must really know this by now, is that the dot product measures similarity because between objects. Because it's the dot product is the cosine similarity. Okay, so this is really super important to understand this, to know that dot products are a similarity. Now, if I use here, so this UWO, this is like the embedded context word, and this is the embedded center word. So I take the dot product of the embedded center word and the embedded context word. Should it be a big value or a small value? Should they be similar or not?
Yeah.
Yeah, they should be similar because context and center word should be recognized as something similar. Okay, so we put this here. So big value means bigger than 0 and can be towards infinity. We put this into a sigmoid, and the sigmoid will take a value for positive values, it goes to 1. For negative values here, the sigmoid goes to 0. And for a value of 0 here, it has a value of 1/2. If a dot product is 0, it means that these vectors are orthogonal. Okay, so that means that they are not specifically related, but they are also not opposed. So this here is, so the sigmoid gives us a value between 0 and 1, and the logarithm of something that is between 0 and 1 is negative. So the negative logarithm is something positive. So this is a kind of, okay, and if they are super similar, okay, so if this generates a huge value, we get sigmoid of something huge, this is a 1, we get a logarithm of 1, and that gives us a penalty of 0. So here, value of 0 and 1 of 0 because we're minimizing. This is something negative, okay? But we want to, this is something positive, and we want to get it to as close as 0 as possible. And we achieve this if these 2 are pointing into the same direction. And here, so this is for the context, for the center of the context word. Now here we have the center word embedding and the negative sample embedding. So this is a word embedding of a word that is just, it's a random word. Shouldn't be too related to this guy here. So we now take here, this looks a bit strange, so we just take a dot product between the random word embedding and the center word embedding. Should these be similar? Not at all, or at least not specifically. So what we now do is that we take the negative value of this, because now we don't want them to point into the same direction. We don't want that a random word embedding also points into the same direction as the center word. Okay? The contrary, we want it to be somewhere else. And this is why we use a negation here. And then we have again the same logic. Okay, so if these are highly unrelated, then we get originally a negative value, and the negative value is negated. So we are a large positive value, and the sigmoid of a large positive value is 1, and the logarithm of 1 is 0. So here we make sure that unrelated or random words will have a representation that goes really into a very different direction. Okay, so together we make sure that similar things are close together and unsimilar things. And what makes similar? Because they occur in similar parts of the text, of the original text. And other words are somewhere else. Okay, so this answers the question, okay, what could be a loss function in general? If we don't have a specific task, but still we want that similar words are located in a similar position and unsimilar words are not. Okay, and when we did this, well, we can, typically now we can train this in a neural network. And this is what you do at home. And what you typically then do is that you stick only with this W matrix. Once you train it, you use only this first embedding, the center embedding, to embed the words. But you can also take the average between these two. Both are possible. Okay. So I did this already for my example, and with exactly this approach, after 100 epochs of training, you see that it puts bus, car, and bike into one corner and the food in another, and there's like other words that are not part of the vocabulary that can occur in the text, and they are not part of this debate. Okay, so what was here the basis for training? So I used some. So here I use these texts, okay? I asked, in this case, I just asked ChatGPT to generate me some texts, some sentences with burgers and so, but if you can get them from websites or it doesn't matter. You have just some text here. I have 20 sentences that talk about food, okay? I have 20 sentences that talk about vehicles, yeah? And then I put them together here. And this is my my corpus. And then I use these 6 words as my vocabulary. Everything that is not one of these 6 words is just unknown. It's not relevant for me. Okay. And then I employ, I create the database according to what we just did. This is a function that you have to create at home. Then I have this this logic of the embedding that I can train the model. And after I do this, then I get this figure. Okay. So this is an explanation of how I can get to an embedding without a concrete task at hand.
Sorry, in this case, I think that you're using 2 variables. That's the case. What I want to know is that if there's some kind of automatic way to to give some kind of automatic explanation of each variable, I think that we could roughly say that both of the variables represent an axis between mode of transportation and food.
What do you mean with the 2 variables?
Because we're using a two-dimensional graph.
I mean 2-dimensional. Okay. So you're asking about what's the semantics of these 2 axes? There is no semantics.
No, what I want to is that, like, if there's some way to automatically give tasks.
I'm sure that people have looked at that. Absolutely. Absolutely. I mean, I don't know, but I'm sure that people have done it. So, I mean, what would I do? I would do, in this case, I would do clustering, and then I would, or you can somehow train a decision tree or something like this in this space. Probably now thinking about what people today would probably do would just need to take a screenshot and show it to ChatGPT, and he would create you some explanation.
It's not a particularly bad idea.
Yeah. Okay. Okay, but I hope that you found this interesting, and now you know what an embedding is and how roughly this would work in PyTorch. But of course, without having seen more code, it's very important to practice that. So very good that we have a sheet that will be online in a couple of minutes, so that you can practice this at home. Very good.
Sure.
Okay.
Thank you.
Okay.
Profe, ahora que ya podemos hablar español.
Speak your language. No, sí, dale.
Es que lo voy a mencionar, es interesante. Pues, volviendo, es que me quedó sonando mucho el nombre del municipio. Y no sé si de pronto la idea que yo tenía en la cabeza se puede hacer a través de embedding. Y es muchos datasets de los municipios. Mucha buena parte de la información que maneja la administración pública es data no estructurada. Son textos, documentos, un montón de cosas. Y cuando hay data estructurada, hay momentos en los cuales se refiere a un municipio o se refiere a una vereda, por ejemplo, pero no hay forma de convertir esa información blanda, por decirlo así, en algo que yo pueda contabilizar de una forma más eficiente. Entonces, no sé hasta qué punto se puede hacer algo similar, pero para encontrar la similitud de, o sea, poder medir de alguna forma la similitud legal de los municipios de acuerdo a sus características sociales.
Pero es por departamentos.
Pues yo
Si haces un encode de 1000 y pico a 32 y miras qué podrías hacer ahí.
bueno, pues
Sí, no, sí,
Eso me va a servir algo de una manera útil. Porque, mira, estamos hablando inclusive de gráfica, de imágenes de acción, sí. Que necesidad hay de generar embeddings para ellos. Hay necesidad que no. Pero si tú puedes agrupar imágenes o mapear imágenes que tienen ciertas similitudes en áreas similares, eso ya es útil.
Lo que hizo Alfire.
Sí, sí, hay varios. O sea, hay varios bibliotecas para image embeddings, visual embeddings. Entonces,
Pero hay una cosa solamente para que lo tengas en cuenta, es que, o sea, dependiendo del corpus, uno dice similaridad, son cosas que se le parecen a uno semánticamente. Pero es que esto captura es, en este caso, coocurrencia. ¿Sí?
correcto.
O sea, y eso no quiere decir que necesariamente se parezca. O sea, lo que quiere decir es que aparecen repetidas, o sea, de manera repetida dentro del corpus, pero yo puedo tener, o sea, por ejemplo, es que ayer estaba haciendo un ejercicio precisamente con WordTube y generé un espacio donde puse la palabra inteligente y estúpido como vector de comparación y después puse inteligente y lo que más salía al lado de inteligente, perdón, de genio, genius, era full or something like that. Porque muchas personas cuando hablan de una cosa hablan de la otra. Entonces hay mucha ocurrencia de la palabra genio con la palabra estúpido.
Claro.
Y entonces uno dice, ¿son similares? Desde nuestros puntos de vista semánticos no son sinónimos. Pero como aparecen tan seguido en el corpus, pues él los comienza a poner en... A lo que voy es que con los municipios,
Sí,
o sea, tú necesitas entender, o sea, tú quieres decir, venga, quiero que esos municipios que se parecen aparezcan en un espacio de representación.
Pero
El tema es tu corpus, que
Pues,
dice,
claro.
no del record, sino cómo, o sea, aquí tú defines cómo va a ser el embedding. Entonces, es hacerlo o sea, depende de cómo defines tu función de Perl. Entonces, si tú haces esto, vas a poner cosas juntos que ocurren mucho. Sí. Y eso es útil si tú después quieres, por ejemplo, generar lenguaje natural, porque tienes que saber, pues, cuáles son palabras razonables que ocurren mucho. Entonces, si tu tarea es producir texto, eso es muy útil. Pero si tu tarea es otra, pues deberías tener, o sea, por ejemplo, no sé, quieres un léxico, quieres o significados similares, ¿sí? O sea, algo más semántico y no tanto por concurrencia, pues eso tendría que reflejarse de cierta manera en la función de Perl para que lo aprendas.
Sí, por un lado,
Entonces, hay unos embeddings que funcionan mejores para algunas tareas y otros funcionan mejores para otras, inclusive para el mismo conjunto de objetos.
O sea, esto es full NLP, ocurrencia, texto, semántico.
En este ejemplo, pero tú puedes hacer lo que tú quieras, o sea, puedes definir tu propia función de... Eso es un ejemplo de cientos de embeddings que han sido definidos. Y eso es para concurrencia, sí.
si te debes mantener, es como arman los pairs, como armas esas parejas de lo que quieres que aprendan.
Yo tengo una pregunta. Yo podría combinar esto, o sea, estos son categóricos, todo, ¿cierto?
Sí, aquí yo trato mis palabras como categorías.
Exacto. Pero yo podría combinarlo como para tener como autoefecto, o sea, como que ciertos categóricos están influyendo en el numérico.
Claro, o sea, si hablas ahora, este último ejemplo solo fue cómo aprendo yo un embedding para un atributo particular. Aquí un atributo que codifica una palabra. Pero en tu base de datos original, tú puedes tener una mezcla de todos tipos de atributos y por eso tenemos aquí los combines. En ese caso, tu embedding layer sería, para las palabras, sería uno acá, pero usa otros atributos aquí, los combines.
Si, por ejemplo, tú quieres hacer un embedding de tus pisos térmicos. Entonces, tú tienes templado, cálido, frío, y quieres utilizar un algoritmo de clasificación. Entonces, una buena manera de meter información dentro del algoritmo es agregar un embedding que me establezca cierta distancia física entre esas categorías. Era lo mismo del caso ahorita de los municipios. Pues la primera utilidad de los embeddings es que usted, para nosotros, un modo de código de los municipios, usted tiene que tener un vector de 1100 y pico entradas para poder decir uno para Becorral, uno para Tuluá. Entonces ahí es necesario usar los encódigos. Pero la otra también los puedo utilizar como una estrategia de darle signaling, de darle señal al algoritmo también para agregar nueva información que yo la conozco, que está embebida y que de alguna manera tengo que representarse el algoritmo. O también pues que para eso utilizamos Machine Learning, ¿no? Para revelar patrones ocultos de la data. Entonces, pues es totalmente válido venir con maneras totalmente, y puede que no tenga ningún sentido desde la manera en la que conocemos la data, pero si funciona para el algoritmo, pues hay que hacerlo, porque pues es lo que queremos, ¿no? Bueno, al final el embedding es una oportunidad de introducir más información al algoritmo de Machine Learning.
De pronto, algo que podría pasar es que si uno utiliza un embedding similar a esto, utilizando municipios, lo que va a terminar ocurriendo es que va a terminar siendo un proxy de la ubicación geográfica. Si uno utiliza como corpus, información. Si utilizo, por ejemplo, guías de transporte, no, claro, agarra la Chiaca y Cam. No, agarre no sé, la Cali y Buenaventura.
No depende del corpus, sino de la función de pérdida. La función de pérdida codifica cómo van a ser las relaciones, no el corpus. El corpus lo influye, pero son las dos corpus que tienes disponible, pero sobre todo la función de pérdida, porque tú con el mismo corpus puedes aprender otro embedding si tu función de pérdida es otra cosa.
Ok.
El poder le metió hasta textos de Wikipedia. O sea, cogió imágenes satelitales, imágenes de radar y textos de Wikipedia.
Ok, como guardo el corpus. ¿Y cuál fue el resultado? O sea,
Un embedding por cada píxel de la imagen satelital. Tu imagen satelital tiene píxeles y ese píxel tiene un embedding de, no sé, 40 dimensiones, una cosa así,
o sea,
que representa semánticamente algo. Entonces, ya sabes que si coges este píxel y calculas distancia coseno con otro píxel, da igual, pues las coberturas son iguales, pero hay más cosas que el embedding te está diciendo. La similaridad es de la cobertura más la descripción que se hizo en Wikipedia más otra cosa.
pues entonces yo podría agarrar cualquier píxel de la Tierra, es como un raster global o algo.
Sí, sí lo sacaron para todo el planeta y lo van a sacar anualmente y es temporal, es decir, está desde el 2010. Entonces puedes ver, por ejemplo, quiero definir cambio de coberturas. Pues comparar los embeddings del año pasado con los de este.
Entonces significa que también yo puedo hacer consultas.
Sí, sí.
Debería poder hacer una muy buena consulta conversacional.
¿Perdón?
Yo debería ser capaz de hacer una muy buena consulta conversacional. O sea, yo le puedo decir, cuéntame la historia de este píxel.
Ese es otro tema. O sea, aquí lo que tienes son números.
Mira, comer lechuga. Gracias. Comer lechuga, comer lechuga.